titrations, and I really wish we were in class for this because they're so much fun to do. Titrations are a way of determining concentrations of acids and bases when we don't know what they are. And typically, in our lab, what we do is react strong acids and strong bases together. And you might remember from grade 10 that this is called a neutralization reaction. When you react a strong acid with a strong base, it always reacts to form water and a salt. Now, a salt is just what chemists call an ionic compound. Sometimes that salt, as in this first example, is table salt, but other times it can be other salts like potassium sulfate or whatever the remaining two ions are once the acid part, the hydrogen from the acid, has reacted with the hydroxide from the base. So watch when we're doing our problems. If you see an acid reacting with a base, what I want you guys to do is to start by writing a double displacement reaction. Now, when we did ionization reactions, we just showed how things separated to ions. We only ever took off one proton at a time. But when we do a double displacement reaction, what we want to remember is that hydroxide on the base is actually strong enough to rip off all the hydrogens from the acid. So we're going to completely neutralize it by removing all of the hydrogens. So we're going to get to balance our reactions. Now, if we're going to do a reaction between weak acids and bases, we're not going to get a complete neutralization. When we react a weak acid and a base, a reaction called salt hydrolysis happens. And that results in the resulting concentration being a little bit acidic or a little bit basic. And it pretty much happens the way you would expect it would. If I reacted a strong acid with a weak base, well, my resulting solution stays a little bit acidic. And if I react a strong base with a weak acid, then my resulting solution ends up a little bit basic, just as you'd expect. So let's take a look at how this would happen. Here's a great example of acetic acid, which we know to be a weak acid, and it's going to react with sodium hydroxide, which we know to be a strong base. Now, the first step is going to be the same as always. We're going to get a neutralization reaction. The hydroxide part of the base is going to neutralize the acid part of the acid here, the hydrogen, which makes it an acid. And that reacts to make water. But the kicker here is the salt that's formed. Remember I said salt hydrolysis? Well, salts we know dissociate in water completely. They dissociate to form, in this case, the acetate ion and the sodium ion. But this ion here, our acetate ion, is the conjugate of a weak acid. And the conjugate of a weak acid is a moderately strong base, which means that it's going to act in water as a proton acceptor. Pull the hydrogen off of the water to reform acetic acid, which is a weak acid and doesn't affect the base our pH very much. And from the water, we now have a resulting increase in hydroxide ions. Now, in grade 12, all of the reactions that we're going to be doing in our class are going to be with strong acids and bases. As you move on to university chemistry, you're going to have to go through these steps, these 3 steps, to figure out the resulting concentrations when you mix weak acids with strong bases or weak bases with strong acids. However, let's just focus on the strong acid, strong base scenario. Consider hydrogen chloride, hydrochloric acid reacting with sodium hydroxide, or sulfuric acid and potassium hydroxide. These are both reactions that are strong acid, strong base. What's really important is you notice they're not always a 1-to-1 ratio. In the case of hydrochloric acid and sodium hydroxide, the 1 hydroxide from the base will react with the 1 hydrogen from the acid. So it's a 1-to-1 ratio. In the case of sulfuric acid, because sulfuric acid has 2 hydrogens, it's going to require 2 hydroxides. I'm going to need twice as much potassium hydroxide. The key when we're doing these is that you're going to have to balance your reactions. And in fact, when we're going to do our calculations to figure out our unknowns, if you haven't balanced your reaction, your calculations won't work. So I really want you to remember to do that. Now, before I get into showing you the math behind this, let's explain what this titration is and where the numbers that we're going to use will come from. This image is a picture of a titration setup. You can see that we have a tall tube called a burette tube, and it's attached to a clamp. Now, in the lab, I quite often like to use double-sided clamps with two tubes. I might put acid in one and base in the other. Burette tubes are some of the most accurate measuring devices we have in our lab. And we're going to need to have a flask. We like to use Erlenmeyer flasks to catch our acid and base because you can swirl them without the water, or liquid, I should say, inside splashing up the sides and ending up all over your counter. You're going to need some acid and base, and you're going to need an indicator. Remember, indicators are chemicals that change color when we are in acid or in base. At the bottom of your burette tube, you'll notice a little valve called a stopcock. In this image here, we see the stopcock is at a right angle to the tube, so that's the closed position. When we twist it so it is parallel to the tube, that is considered the open position. It's important that you always start with a clean burette tube. We would often rinse it first with distilled deionized water to get out any remaining chemical from a previous titration. But then we push through a little bit of the chemical, the acid or the base we were using, through the tube, so that if there was any water stuck to the sides of the burette tube, that it got pushed out. We weren't accidentally diluting anything inside our burette tube. You can see in this image how sometimes little bits of water would like to adhere to the glass side of the tube. That's called cohesion and happens often when we have very polar substances. Now, when you fill your burette tube and you take a measurement, I always want you to do a measurement to the bottom of the meniscus. You'll notice here a great image of a meniscus. The meniscus is where the liquid inside the tube is kind of sticking up the walls of the tube. And you can see that there's a difference of about 2 or 3 milliliters here, depending if you measure the top or the bottom. The accurate measurement is at the bottom of the meniscus. Anytime we do any kind of reading in a tall, skinny tube, whether it's a burette tube or even a graduated cylinder, we always measure to the bottom of the meniscus. In the bottom, in our Erlenmeyer, we have a measured amount, a very accurately measured amount of the substance that we're titrating. You can measure it with a pipette, which is a very accurate measuring device, or if you're using a double-sided clamp, you might have some of the acid or base you're titrating in your other burette tube. You could use that as your measurement. You also want to have an indicator in there that will change color when the endpoint is reached. In this case, there is an acid in the bottom container in our Erlenmeyer, and the indicator they're using is phenolphthalein. Phenolphthalein will go from clear and acid to just pink at the moment that it turns basic. So at that moment, we know we've neutralized all of the acid, and that following droplet was enough to turn the solution basic. Doing titrations is a two-handed operation. With one hand, you slowly drop in your substance that you're using for your titration, and with the bottom hand, you'll be swirling your Erlenmeyer so that it continuously mixes. You'll notice that the color change happens at the point of contact and will persist longer and longer as you reach the end point of your titration. At the moment where the color stays and does not disappear, you have hit the end point of your titration. Consider now that we were doing a titration with hydrochloric acid and potassium hydroxide. You always start with a balanced equation. We can see that 1 hydrochloric acid reacts with 1 mole of potassium hydroxide to form potassium chloride salt in water. We know in this particular example that we ended up using 25 mils of 1 molar potassium hydroxide solution. 25 mils is 0.025 liters. Multiplying that by the concentration, we see that we've neutralized 0.025 moles of potassium hydroxide. Since potassium hydroxide and hydrogen chloride react at a 1-to-1 ratio, I will need 0.025 moles of hydrogen chloride to fully neutralize it. In the question, it tells us that we ended up using 0.45 molar concentration of hydrogen chloride. Multiplying the amount of moles we need times the molarity gives us that we would require 55.6 milliliters of this acid. Now, this is a step-by-step approach that can be used to solve questions, but there is an easier shortcut. There's a formula, VaCa equals VbCb, which works anytime we neutralize strong acids and strong bases. You cannot use this little shortcut for weak acid bases, but again, we won't be using those in grade 12 chemistry. VaCa equals VbCb is just the starting point to this calculation. Our balancing also becomes important. Whichever number we use in the balancing in front of the acid, the number 1 here, ends up becoming a multiplier in front of the base side of the equation. Whichever number we used with our base, in this case potassium hydroxide, becomes the multiplier in front of the acid side of the equation. So this allows us to adjust for when our ratios are not 1-to-1. In this question, the volume of the acid is what we're looking for. Its concentration was 0.45 molars. The volume of the base was 25 mils, and its concentration was 1 molar. This reaction is even easier for us to do using this formula because we don't have to switch to using milliliters into liters. You will notice that in both cases we get the same answer of 55.6 milliliters is required. Let's do this last example together. In this solution, we're going to start by measuring 25 mils of sulfuric acid, and we're going to neutralize it by using 18 mils of 1 molar sodium hydroxide. How do we find the concentration of our sulfuric acid? We know it's a strong acid, strong base, so I can use my VaCa equals VbCb formula. But in order for us to do the calculations, we first must complete and balance our reaction. When sulfuric acid reacts with sodium hydroxide, it forms sodium sulfate and water. I always find it easier to balance reactions if I write water as HOH. It allows me to separate my balancing from my hydrogens and my hydroxides. But either way, we're going to get to the same result. 2 sodium hydroxides are required to react with each 1 sulfuric acid. Because the 2 is in front of the base, in our formula, we will now put a 2 in front of the acid. No number in front of the acid is the same as 1, so we could write a 1 in front of the base. Substituting the values from our equation. 25 mils is the volume of acid used, the volume of base 18, and the concentration of the base 1 molar. We can calculate now the concentration of the acid as being 0.036 molar concentration. I have lots of practice for you guys. There's practice in chapter 18 of your textbook. There's practice on a worksheet you guys have called Ka percent ionization and titrations, which has a few titration questions and also some great throwback questions with extra practice on Ka and percent ionizations. Beneath this video, you will also find a link to the video that I've referenced as we've gone through with the images that you saw. And with a little bit of practice, hopefully you'll be able to do titration questions and calculations of unknown concentration in no time.